Hi class, welcome to the continuation of our lectures in electrodynamics. And again, our main reference for the lecture is Introduction to Electrodynamics by David J. Griffiths, and this book is recommended for you, highly recommended, to guide you in understanding of the following lectures. So to continue, we start with integration by parts. So here you have a technique presented known as the integration by parts, or IBP. We use this very commonly in our solving of the problems in electrodynamics. So if you have two functions, product of two functions, if you get the derivative of that, you will have an expression of this form. So when you integrate when you integrate the right hand side of the equation, you also integrate the left hand side. And so if you do that, you will come up with this expression. So of course you're integrating in a limit, specific limit a to b. So you will have an integral of this function and function f, and then you have a second term which is a derivative of a function with respect to some variable x, and of course you're integrating this with respect to dx, and the result will just be this one here. This is just an algebraic transformation from this equation. So it comes from here. So if you put this term to this side, it becomes negative as here, and then you integrate each of the terms here, and then of course this one you have to integrate also, and then you will come up with this expression. So let's look at an example here. Evaluate the integral of this one, integral from 0 to infinity of x e to the negative x dx. Then you have here, of course, you can assign e to the negative x as equal to the derivative of negative of e to the negative x here. So if you look at the formula, you can compare e to the negative x with this term here, and of course your f is just equal to x. And of course you can also do dg equal to x, and then your f would be equal to e to the negative x. But if you do this, you will just make things complicated. So you also have to make a decision which to assign to this function, part of the product here. So as I've said, it's practical to assign e to the negative x with this one than assigning dg over x as that one, because it will just make things more complicated. So you can try, you can actually try it yourself. So you have that, and so this is now the integral, and then you have the integral from, this is your g of x, and then your f, your f here, your f is equal to x, so your df, sorry for that, this is x, so your f dx is equal to 1. So that's why you have 1 here, and so you don't have to write 1 there. So anyway, that's that one, and then you have x to the e to the negative x. So if you evaluate this, to the this x, this is infinity to e to the negative infinity, that will just give you a very small number, so much smaller than the x here, so it would be 0, and then you also subtract it with 0, so you have 0 here, the whole thing. And then here you will just have the integral of this is just negative e to the negative x evaluated from 0 to infinity, and then you will just have 1. So that's how you do integration by parts. And also, if you have a more sophisticated expression involving the del operator, so you can have this derivative. So derivative of f, the del, or the divergence of f times a, where a is a vector function, f is an ordinary function, then you will also have this one. And when you integrate that, you will arrive at this expression. And looking at this, you have this expression here. By using your Gauss law, this is also equal to this one here, so that you can actually write your integral here as this one. So I'll just this one. Yeah. So in this case, you are using the Gauss theorem to find the integral of this. You just have to associate an integral later on in solving some problems with this one, with this expression here, and then if you find that, you will be able to easily integrate it using this expression. So we will now go to curvilinear coordinate system. So we're done with the rectangular coordinates x, y, z, where the x hat, y hat, and z hat are facing or are directed in constant direction, where the x hat is always in the direction of positive x-axis, the negative x hat is in the negative x-axis, the y hat is always in the positive y, the negative y hat is always in the negative y axis, and so with the z. So we're now going to do, or we're going to investigate curvilinear coordinates, and there are two: spherical polar coordinates and the cylindrical coordinate system. So we'll start with spherical polar coordinates. And the spherical polar coordinates have variables r, theta, and phi here. So if you have a point P, so there's that point P has a distance r from the origin, and that distance r is the magnitude of the position vector towards P. The theta is the angle measured from the z-axis, and that's called the polar angle. And then you have the azimuthal angle phi, and that's measured from the x-axis to the projection of the vector r towards P. So if we expand this, you have theta is measured here. So P is a point in space. P is of course determined by x, y, z, and this time in polar coordinates your P is also determined by r, theta, phi. So theta is measured from the z-axis, and then your phi is measured from the x-axis towards the projection of this r vector towards P. So you have our projection on the xy plane. So your phi is there, and so so anyway, what's important here is to look at the theta hat, r hat, and the phi hat. So r hat is just the direction radially outward from the origin, and so it's lined here, lined in this direction. So your r hat is a unit vector that's in this direction, and your theta hat, so your theta hat is measured in the z direction. So if your P is here, your theta hat would be perpendicular to the r. Your theta hat is perpendicular to the r, and your phi hat is measured here, and this should be perpendicular to this line. So you have a so theta hat is perpendicular to r hat. Theta hat is also perpendicular to r hat. I mean, phi hat is also perpendicular to r hat, and of course theta hat is also perpendicular to phi hat. So they are mutually perpendicular, and for every point that you have, so for example, you have another point. So we will see. You have another point here. So you will have a distance r from here, r prime maybe. So your r prime hat would be this one. It's different now to r hat. And then your z hat would be here. I mean, no, your theta hat prime. So they should be perpendicular. And then your phi would be here, phi hat. So they're still perpendicular to each other, mutually perpendicular to each other. So what can you conclude with this? Every point has a different set of mutually perpendicular unit vectors, theta hat, phi hat, and r hat. So this means that the unit vector r hat, phi hat, and theta hat are not constant. They are position dependent. Unlike x hat, y hat, and z hat, where they always point in the same direction, your r hat, theta hat, and phi hat simply does not point in the same direction for another point in space. So we look at again, we zoom again the figure, and this one here is supposed to be your z. And if we look at this, your z is just equal to, this is also your z, and this one is equal to r r cosine theta. That's your z. How about your x? This one here is your x. This is x, or this is also x. So x would be, what is this projection here? The projection in this one here is just r. This projection here is just r sine theta, right? Because this is also the same as that, and this one is r cosine theta, this one is r sine theta, this one is r cosine. So this is r sine theta. So your x would be r sine theta, and your x would be cosine phi, and your y is equal to r sine theta. This is your y, also this one, that is your y, this is your y also, r sine theta sine phi. So you will have the equivalence of the rectangular coordinate system and the spherical coordinate system. Also here you can also check from here. You can also say that r is also square root of x square plus y square plus z square. There. And also And also your theta would be also has or your phi would be some tangent also. But anyway, let's look at that later on. So that's your x, y, and z. And the vector a, instead of writing with the rectangular coordinate system, instead of writing with the x hat, y hat, and z hat, you can express it in the form of r hat, theta hat, and phi hat, which is this one. So you have the radial, polar, and azimuthal components of A. So in terms of the Cartesian coordinate or the rectangular coordinate system, you have r hat equal to sine theta cosine phi x hat plus sine theta sine phi y hat plus cosine theta z hat. So you have this, as you can see in the figure earlier. And then of course your theta hat would be this also, and your phi hat would be this. So if you dot r hat with theta hat, this is supposed to be 0, and also r hat dot phi hat would be 0, as well as theta hat dot phi hat would be 0 as well. So you can write that in matrix also, in matrix form. This is just this one here. The reverse matrix for transforming r hat, theta hat, and phi hat to x hat, y hat, and z hat would also be this one. As you can see, this is just the inverse of the inverse matrix. And anyway, the inverse of that would just be the transpose of the matrix. You will learn that later on in your mathematical physics. So there are some warnings for this coordinate system. You have, again, as I've said, each particular point in space have a different set of mutually orthogonal r hat, theta hat, and phi hat, and they change direction as p moves from one point to another. And your r is actually dependent on theta and phi, because as the point changes, theta and phi also change, I mean. There's another warning. The spherical unit vectors are functions of position, so beware in differentiating the spherical unit vectors, because for example you will have this here, the derivative of r hat with respect to theta is just theta hat. And also the spherical unit vectors are r hat, theta hat, and phi hat cannot be taken outside an integral, unlike this one, which are constant unit vectors. So what is the infinitesimal displacement in the r direction? So that's just simply dr. So your infinitesimal displacement for in the direction r, I mean, is just dr. How about for the infinitesimal displacement for associated with theta hat? So this is your r, this one is your r, your dr is here, that's your dr, and when you displace, or when you move a bit from r by an angle d theta here, your displacement of this point, your displacement of this point to this point will just be r d theta. That's r d theta. Actually, that's you have the sector, right? Or the circumference of a circle is pi, 2 pi times r. 2 pi is the angle of the whole circle. So when you have a circle with radius r, and this is just theta, the sector here, the sector is just actually equal to theta times r. If you are referring to the whole circle, then your theta will just be equal to 2 pi. So here, if you get the derivative ds, this is d theta r d theta plus theta dr. But the ds here, you have only in this direction, so only the theta changes, because the r here would be the same r, so the derivative of r would just be 0 because r stays constant. So your ds would be r d theta, or your dl theta is r d theta, which is this one here. Now for the dl phi, or the displacement associated with the azimuthal. So this is r sine theta, as we have seen earlier. And so if this r sine theta will move some d phi, then of course this one here, or this one, would be, so that would be d s equal to r sine theta d phi. So that's that one, or this one here. So in general, the infinitesimal displacement dl in the spherical coordinate system is this one here. The components in spherical coordinate system. But of course, that's dl would be dx x hat plus dy y hat plus dz z hat in the rectangular coordinate system. But this one is in spherical form. The infinitesimal volume element then would be this. But in this is also equal to dx, dy, dz in rectangular coordinate system. And your dA would be this one. dA, for example, here you have r sine d theta dr for the direction r hat. For the direction theta hat, what would that be? So that would just be dr times r d phi. This is the area for theta hat. How about for the phi hat? So this would just be this is this one here. So for the phi hat, that would just be what? This is dr times r sine theta d theta. Oh, I'm sorry. This is not so anyway, this is r sine theta d phi for phi hat. So you have r sine, no, that's not d theta but theta. R sine theta d phi, d phi. Sorry, we have made a mistake here. This is supposed to have sine theta, and this one has no sine theta. Because you're supposed to have this one and this one, and this one is r sine theta. So this has to have sine theta. In the general case, but when your theta is pi over 2, then sine theta would just be 1, so you will have only this if the surface lies in the xy plane. So the radius r ranges from 0 to infinity, from the origin to any point in space. The phi ranges from 0 to 2 pi, and then that already covers everything. If your pi ranges from 0 to pi, not 2 pi, because if you go 0 to 2 pi for theta, you will cover the same volume twice. So example, find the volume of a sphere of radius r. So here you have integral, the triple integral, because you have dr, you have dr, d theta, and d phi. And so you can separate r square, sine theta, and d phi. Usually if you have a azimuthal symmetry, then this would be automatic to be 2 pi. And so anyway, in this case, you are integrating within in the correct limits. So the sphere with radius r has a volume of 4/3 pi r cubed. So how do we translate the gradient or divergence or curl and Laplacian into spherical coordinate system? So in this case, you have following the rules of calculus, you have the partial derivative of t. The partial derivative of t with respect to x would be this one here, because you have now the spherical coordinates, then it is customary to have this one, and this one. The total derivative with respect to x would be the total partial derivative of t with respect to x would be this one, because here you can actually cancel and have this. You can cancel that and have that. And if you cancel this two, you only have partial of t with respect to x. But your r is also a derivative, it's a function of x here. So you can actually get the derivative of r with respect to x by assuming theta and phi to be constant. And so if you do that, well, it takes time to do that. You can prove it by yourself, and if you are able to do that, then you'll be able to find that the gradient can be written as this one, and the divergence can also be written as this one, the curl, and of course the Laplacian. You don't have to memorize everything. However, you should be able to do how it's done. It takes time to show this, but if you have the time to show it, then to prove it, then it's well, it will give you some conviction. So we'll go to another coordinate system, and this is the cylindrical coordinates. And in this case, you have a point P where you have a point that has it's the S is the distance from the z-axis, S, or that's also the radius, or that's the distance from the radius of the cylinder. I mean, it's also associated with that. So you have S pointing in this direction, S hat, and of course your phi again in that direction, and you have the Z coordinate system, which is the same as in the rectangular coordinate system. It's always in the Z, positive Z direction, and the negative C would be in this direction. So this one is phi, and then you have S. They are also mutually perpendicular to each other. And the relationship, let's look at this. The relationship is for this is S, and then Z, the Z would be just Z, and then your X would be, or X here would be just cosine of phi, S cosine of phi, and then your Y is of course S sine of phi. So in this case you will have, if you check out the figure, S hat should be perpendicular to the phi hat, S hat is also perpendicular to the Z hat, and then your Z hat would or should be perpendicular to your phi hat. The same as the spherical coordinates, the cylindrical coordinate system also has different set of mutually perpendicular unit vectors at every point, because it's dependent on the angle phi. So again, you can write this in matrix form as hat phi hat Z hat is equal to cosine phi sine phi 0, negative sine phi cosine phi 0, 0, 0, 1, x hat, y hat, z hat. That's the equivalent matrix, or the matrix transformation. If you transform x hat, y hat, z hat to the cylindrical coordinate system. In the same argument as used in the looking for the displacements in the spherical coordinate system, we can also use that in the cylindrical coordinate system. However, this is much simpler than the previous one. So you have these associated displacements for the different unit vectors. And so the dl would be this one, and of course you just multiply everything to get the infinitesimal volume. The range of S is of course 0 to positive infinity. Phi goes from 0 to 2 pi, and Z is from negative infinity to infinity. So you can extend the cylinder above and below. So in cylindrical coordinate system, your gradient, divergence, and curl and Laplacian will have these expressions here. It's not as messy as the spherical coordinate system, but of course each of these coordinate systems that we have, the rectangular, cylindrical, and spherical coordinate system, have their own advantages in solving the problems. Okay, let's proceed with the Dirac delta function. Dirac delta function are also very useful in looking for solutions of electrodynamics problems in electrodynamics, because this will simplify things. So for example, if you have a function of this form, and this function is of course geometrically represented by this. So as you go farther from this point, you get a smaller and smaller value of v, and of course this is radial. So imagine this is like a sea urchin where the r goes out radially from the center. When you calculate the divergence of v, you will actually get 0 here, and the integral of divergence of v d tau, since this is 0, would also be 0. But however, if you use the Gauss or the Green's theorem or the divergence theorem, you will find out that the closed integral, which is this one, is equivalent to the integral of the divergence of v that v d tau. This is 0, but this one is 4 pi. So how come that the results are different when they are supposed to be equal? But actually, this integral here is correct. There's a question in this integral. What makes the divergence of v 0 is because you are dividing r square to v, and it blows up when r is equal to 0. So there must be some value at r equal to 0 for v, and its value is infinity at that point. So let's now go back to the integral 1.85. Look at this integral. Here you have that integral, and at that point you have cancelled r squared, and so the integral reduces to this point. So in this case you don't have dependence of the r, so this must be correct rather than this, because this one is dependent of r and this one is not independent of r. And what makes this 0 is because at infinity, but what makes this ambiguous is the r square. So you have an infinite value at r equal to 0, and this one gives you a different value, which is 0, where there is a case where this becomes infinite at r equal to 0, but this one does not depend on r. It does not depend on r, and it gives you 4 pi. So this must be the correct one rather than this. So therefore integral of the divergence of 1 over r squared r hat d tau is equal to the integral of 1 over r square r hat dr is equal to 4 pi. And this can only be given by a Dirac delta function, this one. And there's a note here that no ordinary function behaves like this, and the only function that does that is the Dirac delta function. So let's now discuss the Dirac delta function. For a one-dimensional Dirac delta function, delta x, you can denote it with delta x. You can picture that out as an infinitesimally narrow spike, very thin here, very thin, very narrow. It has this property that at 0 delta x, where x equal to infinity at x equal to 0, and this is 0 when x is not equal to 0. And the total area here covered by the Dirac delta function is equal to 1. So the total area, this means that the integral of x from negative infinity to positive infinity is equal to 1 dx here. So let's look at the properties of the Dirac delta function here. This one here is the Dirac delta function. This is the definition of the Dirac delta function, and of course you will have another definition you can find in the internet. There are a lot of definitions of Dirac delta functions, and some of these are in integral forms. But anyway, the area or the integral of the Dirac delta function from negative infinity to positive infinity would be equal to 1. So there's a note that delta x is not a function since its value is not finite at x equal to 0. In mathematically, they call it a generalized function or distribution. By the way, the Dirac delta function is the limit of a sequence of function that such as rectangles Rn of height n and width 1 over n, or isosceles triangles Tn of x of height n and base 2 over n. So if you decrease the width of this, you will have a higher rectangle, and for this one, if you decrease the base, you will have a higher or a taller triangle. So that's the limit of the Dirac delta function, is the limit of these two. So if you multiply any function to f of x, so this is 0 except at x equal to 0. So at x not equal to 0, delta x f of x is 0. So you have this one here. That's they're equal because the x only has value at 0, so you can set the x argument of f of x to be 0. And so if you integrate both sides, then you will have this. So you can actually shift the spike from 0 to a, such that your Dirac delta function would now look like this, and this would be 0 if x is not equal to a, and infinity at x equal to a, such that your integral of this kind of Dirac delta function, the shifted Dirac delta function, so this is still equal to 1. So the shift would be just like this. So this is Dirac delta function x of x minus a. So the spike is not anymore here at 0, but here at A, such that your f of x times Dirac delta of x minus a would be equal to f of a Dirac delta x minus a. And so if you integrate both sides, you will have this one here. So let's go to an example. Evaluate the integral. Evaluate this integral here. So this is a is equal to 2, and 2 is between 0 and 3, so this must have a value. If 2 is not included in the limit, then everything would be 0. So in this case, this is your f of x, and this is supposed to be equal to f of a, and your a is equal to 2, so this is 2 cubed, so this is supposed to be 8. And now we can check out this property. This property states that if you have two Dirac delta functions, d1 and d2, these two Dirac delta functions are equal if you have this integral. And we can show this in an example. We can show that these two Dirac delta functions are equal, so that in particular, if you let k equal to -1, then Dirac delta of negative x is just equal to Dirac delta of x. So let's do this. You can have a test function f of x. You multiply it with the Dirac delta function kx. So we let y equal to kx such that your dy is equal to k dx. And of course you will have your limit as negative infinity. So if your x is negative infinity, that would be the same for y. And if your x would be positive infinity, that would also be the same for y. But also, if your k is negative, then the limits would have to change. I mean, they're reversed. So if k is negative here, then the limits would be from positive infinity to negative infinity. So if k is less than 0, these limits will reverse. So if we have this one, we change the variables to y, so this one will become your delta y, and your dx will become dy over k, and then of course your f of x will become this one. But the limits, as you can see, is still the same. However, you have positive -1, which depends on the sign of k. So anyway, let's just put the positive negative sign. If you have a positive k, then that would be positive, and negative k would be negative. So this one, the integral of this, as we have mentioned in the previous slides, this is just equal to f of 0. But of course you have a factor here of 1 over k, and in order to get the ambiguity of positive negative, we can put the absolute value sign for k such that we have everything positive. So this one is also equal to this. F sub O is also equal to this. We can just put 1 over k inside because that's just a constant. So therefore we have delta kx as equal to 1 over k delta x, 1 over absolute value of k delta x. So for the three-dimensional delta function, you just multiply the three delta functions of x, y, and z, and the integral of overall space will just be equal to 1. So if you have a function which is a function of vector, then the integral would just be this one here. So therefore this is a Dirac delta function. That's 4 pi delta cube of r. So you can also do this. By the way, the scripted r is just the difference between r and r prime, as we have discussed in the previous lectures. And of course, the gradient of 1 over r is equal to, as we have solved, here you can get the gradient of this, and of course the gradient of this one, but this one is that one. So therefore Laplacian of 1 over scripted r is just equal to negative 4 pi Dirac delta of the scripted r. So we can now evaluate this integral, and using the identity, the Dirac delta identity here, we can solve that j is actually equal to 8 pi. It's easy. But of course, if you want a solution, a longer solution, you can use the Green's theorem. But of course you will get the same answer. That's of course longer than using Dirac delta function. So you still get the same answer here, 8 pi. So in this example, you have to explain in your in the assessment form. So for the last topic for this chapter, we will have the theory of vector fields. The laws of electricity and magnetism are, of course, expressed in electric field and magnetic fields. But how are these electric field and magnetic fields related to each other? These fields must have some source, and we call this source as a vector. We call this source the potential. It would be a vector potential or just a potential. Like for electric field, we can have the potential, the gradient of the potential, and then for the magnetic field would be the curl of a vector potential as the source of these fields. Suppose that the divergence F, which could represent the electric field or magnetic field, is specified by a scalar function d, such that your divergence of F is d and your curl of F is vector c, vector function c. And since we have that we have that property that the divergence of a curl is always zeros, and so you have the divergence of C as 0. But is this enough to determine F? The answer is not enough, not quite, because we can have an F that like for example, we can have so many F's that aside from the trivial case that F is equal to 0, we can have other functions that can give us the divergence and curl to be 0 everywhere. Like this F and also this F, which you can try yourself. You can compute and you'll find out that they are 0 everywhere. So in order to solve for F, you must have, or we must have, some boundary conditions. So some boundary conditions that we have to consider most of the time is that these fields must go to 0 at infinity or far away from all charges, because charges, they produce electric field, and one of the things that actually they give us the idea that the formula, the Coulomb's law, actually give us the idea that the fields go to 0 at infinity. And of course, the magnetic field, if you have a moving charge at infinity, you will not feel the magnetic field, because again, it is inversely proportional to the square of the distance. So in electrodynamics, that's true, and we always require that boundary condition, especially when we solve Laplace's equation later on in the following chapters. And we can also invoke the symmetry arguments, um, if the normal boundary conditions are not applicable, so we can invoke the symmetry arguments to determine the fields. And so with some information, the Helmholtz theorem guarantees that the field is uniquely determined by by its divergence and curl. So if the curl of a vector f vanishes everywhere, then f can be written as a gradient of a scalar, which is which we have seen in the previous lecture. But of course here your negative sign is conventional. You can do away with the negative. So the theorem, one of the Helmholtz theorem, is curlless or irrotational fields. The following conditions are equivalent. That is, if f satisfies one, if and only if it satisfies all the others. So if you have the curl of f is equal to 0 everywhere, then the integral of f dot dl from initial point A to B is independent of the path, or path independent, so that when you integrate for the whole for a closed path, then the integral of f would be 0, and yes, the gradient of f must be a gradient of some scalar. The scalar potential V is not unique. You can add any constant, and it doesn't affect the gradient, because the gradient of a constant is always 0. So if a divergence of a vector field V vanishes everywhere, then f must be a curl of a vector, and we call this vector potential. We call this the vector potential. And so if you have a divergenceless or solenoidal fields, the following conditions are equivalent. So if you have a divergence of f0 everywhere, then the integral of f dot dA is independent of the surface, or surface independent for any given boundary line. And so the closed surface integral must be 0, and the curl of some vector is, and this one should always be true, and for this one. The vector potential is again not unique. You can add any gradient of any scalar function, and the curl of f, or the divergence of f, would always be 0. So looking at the theorem, f can actually be written as a gradient of a scalar plus a curl of a vector. Here. So anyway, this ends the chapter. We will proceed with the next chapter in the next lecture.